Hello, everybody, and thank you for joining us today. We are just waiting for a few people to still log on to the webinar. So as we give them a few minutes, we'll start in just a couple of minutes. Hello, everybody. Thank you for joining us for this part 2 of our materials testing theory and practice webinar. I just wanted to go over a few quick things before we get started today. So this is a Mecmesin webinar. Mecmesin falls under the umbrella of the Physical Properties Testers Group. Some of the other companies under that same umbrella include James Hill and Alluris. If you're interested in learning more about any of these divisions, you can visit our events page and see the content and on-demand webinars they have available. We also have a technology lab based in Sterling, Virginia and Slinfold in the UK. We established these labs as a way to support our customers through education, proof of concept, and testing demos. We know that a lot of people have changed jobs over the past year or taken on new roles and responsibilities, or even expanded the types of testing that they're doing. So if you do need any assistance with any type of physical testing, please feel free to reach out to us. We can definitely put you in touch with the right person. That being said, I wanted to introduce some people on today's call. Carl Bramley is our presenter for today, and my name is Sharon Smorenberg, and I'm one of the organizers. Then we have various support staff throughout the United States, Europe, and Asia. So if you need information or help, we have someone to assist in your area. And last but not least, we do want to keep things interactive. So please feel free to ask questions throughout the presentation. Click the raise your hand icon and we can unmute you, enabling you to ask your question out loud. Or alternatively, you can use the question box and type in your question. We will read it to the group and provide you with an answer. The webinar is going to be recorded and you will get a copy of the recording to the email that you registered with. If you want to review anything for additional clarity, or if you have a colleague who was interested in attending but wasn't able to make it, please feel free to pass that along to them. And with that, I will turn it over to Carl.
Thanks, Sharon. Welcome, everybody. This is part 2 of the materials testing webinars. We did part 1 a couple of weeks ago. And what we're looking at here is you get an overall general presentation on what is materials testing and what we use to facilitate testing. Previously, we looked at materials properties and extensometry and things like that. Now what we're going to do is we're going to look at the ancillary equipment that surrounds the testing and the testing frames, and also software that you can use to do it. So first of all, we'll look at grips and fixtures. Now, tensile testing is probably one of the most popular methods of testing, and there are a multitude of ways of gripping the sample. I'll put some common ones on here. Things like wedge grips and vice grips. You have them in pneumatic and hydraulic versions of those. The vice grips obviously rely on the strength of the operator to tighten the grip on the sample. Whereas the wedge grips, although you tighten them on the sample, as the sample increases in force, it pulls the wedge action down, increases the tightening. But if you get samples which are liable to thin and spread, then depending on force, for lower forces, say anything up to sort of 10, 20 kilonewtons, pneumatic grips offer that facility where they'll maintain the pressure of gripping even if the sample is thinning. And then one step on from that is the hydraulic grips, where you do need to apply a considerable amount of pressure to the sample to do the testing. There are other ones we have display on here, things like eccentric roller grips, very useful for testing things like rubbers and elastomers. The roller grip is off-centered, so as it falls and the force increases, it tightens on the sample. But then for things like metals, you've got things like a chuck grip. Some metal test samples have a threaded end, so we have different threaded inserts. Or if you just want to hold typically the round samples by the shoulder of the dumbbell, you can use a shoulder grip. And then other materials like ribbon and webbing, specialist grips for that, ropes, yarns and threads for the textile industry. And then something generic like a pincer grip. And there are even many more types of grips than this that we can facilitate for different samples. And of course, each one of those grips, or the majority of the vice grips and wedge grips and stuff, they have different faces. So faces tend to be interchangeable. And what you will do is you'll select the face based on the material that you're doing. What you're trying to do here is create the maximum amount of friction or surface contact between the gripping face and the sample itself. So the very basic ones, we have pyramid. If you have rounder samples, we have V-notch, which has a slight V indentation in it, suitable for round samples. Cross-cut, where rather than the hashed pyramid, it is a straight cut, which goes against the direction of pull, so it bites into the sample. Diamond coated, wave ones for textile to increase the surface area gripping. For things like paper, we have a line contact, where one face has a bar with a single line going across it, and we have wide and rubber faces. You can also get plain faces. These are quite useful actually for testing some materials where you can bond a surface coating onto the plain face. People tend to use things like sandpaper and wet and dry paper that gives them a bit more friction. That's something you can do with a plain face. So some considerations when you're looking at your tensile grips. First of all, the tests are performed within the grip operating range. Grips are sold or manufactured as well to have a maximum rated force for the grip. This is not just the physical test itself, it's for the structural integrity of the body of the grip. So bear in mind, that's something to consider when you're choosing a grip on your maximum forces involved. Your clamping force is contained within the grip body. What we mean by that is that you'll maximize the amount of contact area between the sample and the face of the grip. You can cause damage to grip bodies if you don't insert the sample correctly and use the whole of the face, or at least up to 80% of the face of the grip. You're pinching the end and you're mechanically straining the grip when it's trying to make contact with the sample. And of course, one of the very important things is your specimen alignment. You need to make sure that your specimen, when you place it into the grip, is both centered and parallel from the top to the bottom grip. You can see on the small picture there, we have on many of the grips on the top, we have a small sliding alignment tool, which makes it a lot easier for operators to set that for the depth of the sample. So when they slide it in the grip, they touch against that and it sets the specimen centered and parallel between the upper and lower grip. Tensile testing, obviously one of the most popular ways of doing things, but also obviously you've got compression testing. Tend to use it. You can use the bottom of the machine and what we call the lower crosshead. You can have matching upper and lower compression platens, or you can mix and match them. Round, square. You can have compression platens that are self-aligning, which does help somewhat with the samples which are slightly irregular or not square. So what to look for when you're looking at doing compression testing. So the plates must be larger than the sample. If they're not, you're more than likely performing a penetration test. So you want it larger than the sample. Also look at the hardness, the surface hardness of the compression plate that you're using. If you were doing compression on steel, you wouldn't want an aluminium plate, so you want to increase the surface hardness of the compression plates. When manufacturing your samples as well, trying to get the ends of the sample as flat and as level as possible will also help with things like off-center loading. But as I said before, you can have a self-aligning plate that does help, and we sort of tend to recommend these for most of the applications. If you're looking at doing high force testing with very small distances in compression, it's probably sometimes better to involve some kind of external deflection measurement. It's normally recommended, because what you have is you have compliance in the system. You obviously have movement in the grips and fixtures. They are, although they are tightened up, they're normally tightened up at the zero force level by the operator when they're fitting them. You can pre-stress them and apply a force to them and tighten them up then to try and remove some of the compliance. You've obviously got movement in the load cell, and to some extent some movement in the testing frame itself. Also, when you are fitting them, if the platens are quite large or the sample is quite small, we do recommend using an alignment gauge to ensure that the sample is centered on the plate. This is nothing complicated. It can be manufactured and 3D printed, but it is a small offset piece that you can put on the edge of the plate, which projects forward. So when you push the sample in, it touches it, you know it's in the same position each time. Bit of a guide for locating the sample. But many systems that aren't using an external deflection, like an LVDT or a deflectometer for the movement, you can compensate for system deflection or system compliance. Many manufacturers do this, and many testing systems. So what you're essentially doing is you're running a test without a sampling. So you're looking at any movement, load cell, grips and fixtures. But you measure this, and you can measure the amount of movement. And once you've measured this, then you can apply that to the test, and it can be used as a compensation offset so that you can get more accurate results from small distance, high compression forces. Another test which is commonly used is the Flexural, the bending test. The two most common ones are the 3-point Flexural test for supporting at either end. We're applying a force in the center of the specimen, or we're doing a 4-point Flexural test where we again support both sides, the lower part of the specimen, but this time we have 2 loading points on the specimen, and these can be at varying distances from the outside supports. It gives a more overall bending, whereas the 3-point gives a point contact. But when you're doing bending tests, excuse me, things to consider. Your span is long enough, the distance between the 2 supports, and the depth ratio. So if you have a very long span and your sample is reasonably flexible, you'll be bending and moving down in the center quite a lot. You've got to make sure that those supports are high enough as well. Your support radius, both on the bottom and the top one we tend to call the nose, are they wide enough and are they hard enough for the sample that you're testing, particularly if you're doing something like a metal or a ceramic. So support height, ensure it doesn't touch out on the bottom. Now, are you going to use direct measurement? So are you going to use the crosshead, which is the measurement on the top of the sample, or are you going to use an external device where you'll measure deflection underneath the bottom of the sample. To say it could be LVDT or deflectometer. Again, this is another one where you could use the SDC, the specimen deflection compensation, as part of the test setup. And in 3 or 4, the peak stresses are produced, as I said, in the 3-point flexure fixture is at the midpoint or point of contact. Reduced stresses elsewhere, so it's a localization of the stress in that area. Whereas the 4-point flexural fixture, it produces a peak stress along an extended region of the specimen, and it exposes it to larger areas for looking for potential defects. 3 and 4 point aren't the only ones. There are other types of bending tests, things like cantilever beams, where you are holding at one end and bending at another. Shear testing is another common method of testing as well. It tends to be used with adhesives and fixings where you're bonding 2 things together. You can do it in tension or compression, and there are many different types of setups for the shear. Those are the 2 simple ones there, a single or a double lap shear. And what you're doing is you're looking at the amount of stress over the contact surface area if you've bonded 2 things together. To do that. But again, there are many different types of shear testing. I'll just cover some here. You see there's different fixturing. The important thing to note on here is a lot of these devices, because it's shear, are always offset. So if you are going to do an offset shear, and if we go back and look at that, you'll notice that the grips there need to be able to remove from both sides of the gripping face. So the vice grips are very well suited to this, because you can move the 2 faces independent of each other. So you can apply an offset. If you look at that picture there, the center line of the loading is down the center of the sample, as opposed to any twisting or bending motion. So there's some things like cantilever shears, rail shears, bolt shears, isopescu shears, where we're taking 2 halves of the sample and applying a force across them to make a shearing action. One of the other things people will need to do is to prepare their samples, and there are lots of different ways of preparing samples. One of the simplest ways, which tends to be done with rubbers and thin plastics, is to stamp out the sample using a cutting die. So you can have various shaped dies. They tend to be down to standards, but people can make custom dies for different applications. And you'll need a die press to press it out. Although you can use the testing machine, because you can mount these dies on the frame of the testing machine and use the machine to stamp out the samples. Although if you've got a lot of throughput of sample testing, it does tie the machine up while you're sample prepping. So a standalone version, it can either be manual or pneumatic, or some people even do hydraulic presses for doing that. Of course, with plastics, you can do injection molding. Some companies sell small injection molding machines for making samples, or CNC profile cutters. They are actually quite reasonably priced now, even for the DIY enthusiasts. So you can use these for cutting out profiles for different materials to the required specimen sizes. And of course, these specimen sizes are all detailed in testing standards. So we look at here as an example of ISO 527. There are lots of different dumbbell sizes. There are 5 or 6 in this testing standard, and they allow different sizes for different types of materials. They are recommended. They have their preferred sizes, although they are not fixed in stone, so you do not have to specifically use that one, as long as you're adhering to the guidance on production of the dumbbell sample, and you're getting your width to diameter ratios and your radiuses of the curve section to the end tabs. So there's some common rules in there, but the majority of people will select one of these from the testing standard. to do their testing on. And each one of these, as I say, does depend on, particularly for something like ISO 527, the type of material that you're going to be testing with. So if we're doing testing, we can test at our standard laboratory temperature, or if the product is going to be used in a harsher environment at higher or lower temperatures, then we have to consider making the environment more suitable for the testing. So there's a couple of ways you can do this. You could precondition the sample prior to testing, transfer it to the testing machine and do the test, although that would incur either heating or cooling of the sample as you move it between the conditioning chamber and the test machine, and it's quite time consuming to do. They're always a little bit difficult when you've got something that's hot or extremely cold to do. So the solution to this is to do it on the testing machine. Now, testing machine chambers, call them a thermal cabinet or a thermal chamber. They're limited in what they can do as far as the temperature range goes. The current ones that we have in the range of plus 280 degrees C to minus 80 degrees C. You can obviously go a little bit higher, but because you're working with a limited space, if you need a higher temperature, you need to start increasing the thickness of the walls of the chamber, which in turn will then reduce the internal working capacity of the chamber. For lower temperatures, you can get for things like sort of down to 20, minus 20, you can get cooling units which bolt on the back of the chambers. And if you need to go much lower, the preferred method is using a Dewar flask with liquid nitrogen storage. There's a picture of one in the center there. And this is basically a chamber filled with liquid nitrogen. And you increase the pressure in the chamber, it naturally boils at ambient. And then that's fed into the back of the chamber under controlled conditions by opening a valve and releasing that as a gas into the chamber. You'll notice also that with the chambers, what we tend to do is rather than tie the machine up to be always used with the chamber, we have it on a rail system. So the chamber is freewheeling, you can lock it off. So you can push it back out the way if you want to do some ambient testing. And then we use different types of rods and connectors from the base of the machine into the chamber. The only consideration if you're considering using a chamber is the amount of room that you have to do the test, because this will be obviously finite for the distance inside the chamber. But that also needs to take into account the size of the grips, the size of the sample, and the amount of elongation of the sample if you're doing a tensile. For compression testing, usually not a problem. So if we get up to, say, plus 280 degrees C, if we want to go higher, then we need to start thinking about furnaces. Furnaces will go up to 1800 degrees C, 2000 degrees C. And on the materials testing machines, you tend to look for what's called a tube furnace. There's some examples of them there. They can be a freestanding that you can mount between the columns of the machine, and there's an open tube there. They do have access ports on the side, so you can actually use extensometry with these, but there has to be specialist temperature compensated things with ceramic arms that can sit outside and go through a port into the middle of the chamber, or using things like capacitive extensometers for looking at the movement. There's also a lot of things to consider now with the temperature. You are in fact connecting it directly to a load cell on a machine, which are strain gauge devices. So at some point you need to consider dissipating the heat between the chamber, and you will need to use specialist materials. What we're also trying to do here is obviously a material that's not so sensitive to the heat, because you're going to suffer from things like thermal expansion within your grips and your rods. But you can null that out if you create your test setup correctly. So as rods and things expand, you can actually make the machine move to null it out and keep it at a constant, as close to zero force as possible on the distance. But we have testing frames that we use for testing, and they tend to fall into two categories, single column or twin column. The single column machines are somewhat restricted with their what we call the throat depth. So this is the distance from the testing area to the back column. But again, they have a small footprint. So if your force range is within, we do them on 5 kilonewton rated and 7.5. So if your sample is okay to be fitted in the shorter throat depth and it's within your capacity, then single columns are fine. If not, then you tend to move to the bigger twin column machines. We do them in 10, 25 and 50 kilonewton rating. That's the rating of the frame, and on the frames you can fit obviously the maximum capacity load cell for the frame, or you can fit smaller load cells. So although it is a big heavy duty testing frame, maybe up to 50 kilonewtons, there's no reason whatsoever why you can put a 100 Newton load cell on it for doing a different type of test. And there's a big range of load cells. You tend to want to pick your load cells relative to the work that you're doing and try and get it within the mid-range of the load cell, so you've got plenty of scope top and bottom for doing your testing. So what do we look for in a testing system? So excuse me, the speed range. Is there adequate speed range in the system for all the tests that you want to do? Typically, for most of the static machine testing, there are very few tests which tend to exceed 1,000 millimeters a minute, and most of the testing ranges will be down in the region of 500 and lower, unless you start moving into fatigue testing, and then you would not probably be using a static system. You'd be using a pneumatic or hydraulic system. Intelligent load cells. In other words, what we're saying is you plug a new load cell in because you can swap the load cells for different applications. It recognizes what they are. It has its calibration data stored in there for the load cell. The stiffness of the frame, as you were saying earlier on, there's the single columns and the twin columns. There tends to be a higher stiffness factor in a twin column than a single column. But if you're using things like extensometry, then the stiffness doesn't come into play as much. Speed resolution, how well you can move between your different speeds and how accurate those speeds are, can be displayed on the machine, and how it will control those speeds. The load cell accuracy. Most of the load cells we use are of reading plus or minus 0.5%. And most of the ASTM standards only call things like a 1% plus or minus 1% of reading accuracy load cell. And your load cell resolution, how many digits can you see on your display and can you report for the size of the load cell there? That also impacts on your calibration range as well. Most machines where you can drive at a distance per time, millimeters per minute, inches per second, but we also have two other ways of driving. We have load rate and strain rate. Load rate control will apply a force over a period of time, and strain will be a distance over a period of time, normally based on an external device like an extensometer. And we support extensometers because very often some of the tests, the testing standards require you to look at the strain readings within the center section of a dumbbell. So we facilitate the use of extensometry. And of course, software. Software probably be the most defining factor on using a test system. And just some visuals there on accuracy, precision, resolution, repeatability, what you're looking for in a system. So whether it's accurate and precise, or it's grouped together but it's not where you want it to be. You can see from the visuals there the definitions of them, and also looking at small increments of measurement. One thing to consider is calibration. So There are various calibration standards. So there are the force verification standards, ISO 7500-1, ASTM E4, and both of these are aligned through European accreditation agreements. And there's also standards for verifying the equipment you use to calibrate as well. Front of a testing machine is quite simple for control. You have normally a display and some control buttons for functionality, the ability to move the machine and position it. And on the Mecmesin in front of the machines, we have a scroll wheel for moving the machine and jog buttons that you can interface with. For connectivity on the back of the machines, we have various ports for digital I/O, for extensometry. We have 3 ports on there, USB connection to computers for software, and guards for interlocking if you're having a guard fitted to your system. So looking at testing standards, some of the most common testing standards, plastics, rubbers, flexural test, metals test, each one of them having the similar partners in the ISO standards and the ASTM standards, all really quite compatible, some subtle differences between them, but they all tend to follow the same format. So you're looking at, excuse me, a scope. Excuse me 1 second, I'll just put myself on mute. Sorry about that. I'm sore throat. So a scope, which is a brief outline, references to other standards, the terms and definitions used within the standard, the specimen geometry, what size specimen you're going to use, and testing conditions, which is the physical test itself, the results you're going to generate from this, and the report, which is the test report at the end of it. And most of them follow the same or very similar formats for the testing. So we mentioned software. The software that we use is called VectorPro. It's our materials testing software. And I'm just going to run a video now and I'll talk over it. I'm not going to take you through all the ins and outs of the software. I just want to show you some features that we think are important, as well as doing the testing, being able to share with colleagues stuff. So the VectorPro software, this is one of my libraries I've got with ASTM standards in there. I put pictures on the front, it's just a visual indication, and so I can see what test is. But if I go and edit this test, I can see from the front. I'll put some descriptions in there, what it's about. There we have our sample dimensions, our test operations for movement, and some results. And they all follow a similar format. But here I've got an export feature. So if you've got a colleague who wants to replicate this, or you have another production facility, and you want to send them, if you created a test that you want to send them, you can email it to them. So I've just clicked on the export, and I'm going to send this one to myself. And if I go back to my email, I've got a link from the cloud there, and if I click on that, it's pulled up a HTML folder for me, and I can see what I've been sent. Then if I want, I can then import it. This does give us the ability to be able to create tests for customers as well and send them out to people, and in the future make them more available on our website. So now I'm creating a blank database, put in a new test in with my name and choose my machine and then import it. I'll log on to the cloud. Incidentally, the cloud's free to register with. And there we go, I've imported everything from that test I can start using straight away. So now I've got a test, but more importantly, if you are testing and you need to share results with people, we go back to that test. There's a single test in there with some results. So I might want to share these with a colleague. So again, I'm already logged into the cloud still, so I can send these to somebody. I'll send these to myself this time again. And go back and look at my emails. And I've got another link in there from the cloud. But this time it's the individual test itself, that test graph. I can export that, and it's asking me to switch over again. I go back to my version, and then I import it. It gives you a slightly different symbol to show that it's been imported from somewhere else, but now I can go and view that. Look at the results for that test. But also with this, we go back and look at the link. Because it's a HTML link, you could send this to anybody and view it on any device. So if we go and look at the actual stress and strain, if we can print these, we can look at different versions of them. We can actually look at the graph itself. It's a live interactive graph. Look at the results. So you could do this on any HTML supported device. I can print this as well. And this is printed to HTML, so it's thrown out everything I need or I want from that test. And then it allows me to select what I don't want, to customize the report. So I'm turning a few things off here to make it a simplified report. You'll notice the top one says QR code, and I'm pressing print. There's a little QR code in the corner, as well as what I've selected. So if you do have a smartphone, a smart device with you that has QR code reader, if you fire that up now, what we'll do is we'll look at the report. I've just created a simple report with some results and a graph. And on the top is this QR code. So if you do have a scanner on you, I'll leave this up for a second. You scan that code, you should be able to get that graph with all the results and everything on your cell phone or on your web-enabled device. So it is a nice little feature on there. Hopefully people have done that. Okay, that's all from me so far. If we've got any questions, I think over to Sharon. She's been monitoring questions coming in.
Thanks so much, Carl. I'll just give everybody a few minutes to gather their thoughts and just remind them, if you want to enter any questions into the chat box, now would be the time to do it. Or if you just want to raise your hand, I can unmute you to ask your question. Let me just take a look and see if we've had any questions that have come in. We've got one, Carl. Should a self-aligning compression plate be fixed or moving?
Good question. It can be either. If you're confident that when the self-aligning plates, they can be fixed in position. But what you can do is bring the two compression plates together, apply a small force to it, and lock it off in that position so you know that the two plates are exactly parallel to each other. A good way of testing this is with a bit of carbon paper clamped in between and move the plates together so you can see if there's any high or low spots. But saying that, they are self-aligning, so if you do leave them slack, it's like a ball and boss system in there. So as it comes down and touches the sample, it will self-align with the top of the sample. So this is also proving the point, is your sample level and made correctly. So it can be done either way.
Thank you very much. And then somebody else wants to know, where can I get sample cutters?
Where can you get them? Mecmesin do sell sample cutters, but there are lots of manufacturers out there. If you type in if you have a particular testing standard and you type in the die reference in there and put sample cutter into Google, there are lots of companies out there that will provide these, both the ISO and the ASTM, but obviously other things like the Japanese standards and Chinese standards as well. So it's a case of shopping around to find a good local supplier. Next.
Great stuff. What class are the Mecmesin force systems?
Yeah, I touched on this earlier. They're a 0.5% class system. It relates to the force measurement. So the load cells that actually themselves, the force measuring devices, are plus or minus 0.5% of reading, not a full scale. When people look at testing systems, they've got things like force gauges on. They tend to be plus or minus of the full scale of the device that's being used, but the load cells are the ones we use. The ELS load cells are of reading, so that's it.
And there's a last question, just somebody wanting to know whether the software is licensed.
Well, yes and no. There is a software license agreement with each software, but it can be used on other PCs. So if a customer is buying a system, then feel free to load it onto your office laptop. For other people within your group, you can take a version of the software and use it. So you could use the facilities that I just showed, where you can share stuff between each other and share results. So yeah, it tends to be an unlicensed, no restrictions on the amount of times that you can use it, because if you're using it with a testing machine, that's its main functionality. The rest is just used for analyzing data and creating tests. If you want, you could sit back. You wouldn't have to be connected to the machine. Sit in your office, create a test program, send it to the office computer, send it to the computer down by the machine, and then go and test that. Thanks.
Great, thank you so much, Carl. I don't see any more questions, but if there are any follow-up questions you'd like to have answered, please send them for my attention at the email shown on your screen, sharon.smorenberg@pptgroup.com. Again, thank you so much for joining us today. We really look forward to hosting you again. Thank you very much.